having established the shear and moment equations for this beam, we now need to determine the rotation. So we'll use this equation. The rotation is equal to the integral of the moment divided by the Young's modulus and the second moment of inertia with respect to x, which in this case is going to be, I'm going to go ahead and not write out 30,000 ksi and 2,000 quatric inches. I'm just going to write them as E and I, and we'll remember what they are. It's the integral of 100 kips times x minus 1,000 kip feet dx, which is going to become, leaving the second moment and the Young's modulus outside, 50 kips x squared minus 1,000 kip feet times x plus some constant integration C1. So now we have to consider our boundary conditions and ask whether we can determine what C1 is. At x equals 0, there is a fixed end. So the rotation at x is 0 has to equal 0. So does the deformation on account of that fixed end. So, given that we've already got an x for every other term, we can go ahead and determine that C1 is 0. And what we're going to end up with for this, I should have scooched that down, is it's going to look like that's got to be 0, or right there, and it's going to increase as we go down. Note that x squared, this term is going to be less than this term as we go up because of how small x is compared to 1,000 or 50. Now, let's use our equation for the deflection. That's going to be the integral of the rotation. Gosh, the stem's on my D's. Which in this case is going to be, well, we'll stick that on the outside again. The integral of 50 kips times x squared minus 1,000 kip feet times x. We said that C went to 0. That is going to become 1 over the Young's modulus in the second moment times 50 kips divided by 3. I'm not going to bother trying to figure that one out. Cube that. Minus 500 kip feet times x squared. We don't have anything in the x term because C1 went to 0. We do have another constant of integration, which I'm going to just pop inside the parentheses for dealing with the second moment of inertia and the Young's modulus. But again, we have a fixed end at x is equal to 0, which means that at y is equal to 0, or at x is equal to 0, y had also better equal 0. So again, in this place, C2 conveniently equals 0. And this is our deflection function. It'll look similar to this as well, even steeper because of the cubic term.